All right, guys, here we go. Third time is a charm, is what I'm hoping. Uh, so, as we tackle this, we'll kind of see what we got going here. So, this is what I got. Uh, we have our linear regression line, and we're talking about what's called the least squares regression. So, this is actually going to be called, you'll refer to it as the LSR. Oh, that's some big bold words right there. Let me write that again. LSR. Okay, so now this is our equation. This is y hat, or the predicted value, is equal to the y-intercept plus the predicted slope and the x value, which is similar to your y equals mx plus b, which is what we've talked about before. You've seen this in algebra, and m is the slope and b is the y-intercept. So it's really the same idea, except instead of being like a line between 2 points, like your y equals mx plus b equation is, we're dealing with a data set right here that we create an x and y with. And we can put that into list one and list two and work from there. So what happens is you get, let me erase some of this stuff. This is from my last video. Uh, we had some, I had some issues last time here. So yeah, it got a little ugly. So I'm not sure. Hopefully, it looks like this may be having an issue here in a minute. So we'll just make this work and go from there. Okay. So what we're ending up with here is this idea that you have a scatter plot with dots all over it, like you have here and here and here and here. And then we do the line of best fit in between. This is what's considered your LSR, your least squares regression line. And I'll talk about that here in a little bit. So let's first talk about how you use it. So we have our equation here. The formatting got a little weird, but it's y hat equals 18,773 minus 0.08618x. And so your slope is 0.08618 here. And it has to do with the thousands of miles that the CRVs were driven and how much they're worth. So if we interpret the slope, it's a negative. So you can see that it's a negative. So it's going to decrease, if you guys notice that. So the value is decreasing at $86.18 for every 1,000 miles it's driven. Or you could say $0.08618 per mile. I chose to make it 1,000 because it's a lot easier to deal with. But you can, either one works. And so if we're looking at the y-intercept, if we go up here to the y-intercept, it's right here, which is pretty much this. And what we're really saying is if we drove a CRV 0 miles, it would cost $18,773. That's all we're saying. Which, trying to find one of those that's 20 years old that is has 0 miles on it is going to be awful hard. So then, how do we find the predicted price? Well, we just take the mileage and we plug in the miles right there. And when we multiply that out, we're going to get a value. And I didn't have my calculator earlier, and I'm not going to do it now. So you just plug it in and you get a predicted value. So let's predict it with 250,000 miles. So we plug in 250,000 miles. I actually wrote down the answer on this one, and we get negative 1,614. So 250,000 is considered what's called extrapolation, and it's basically to make a prediction outside the interval. So I'm going to take you guys back up to the graph here. And if you guys notice, the interval that we have is going to be, let's change colors real quick. Let's go to red. The interval of the dots starts here and ends approximately right there. So like at 85,000 and it starts around 25,000. So 250,000 is way over here. So when we extrapolate it, we're saying that this line continues to go down, and you get way down here at negative 1,614, which is below $0. That makes absolutely no sense. So really what we're saying is, when I go to sell you this car, I'm going to sell you this car, but I'm going to give you $1,600 when I sell you the car. So it makes it a negative value. That doesn't make any sense. So is it a good idea to extrapolate? Yes, but you got to stay pretty close to the interval. So you can't go way out here. So if we would have extrapolated to 95,000, that would have been pretty good. Once we went too far out here, it doesn't make any sense. It won't work. So let's interpret this a little bit. So they give us an equation. The equation is negative, so we're going to decrease here. Let me go back to green. We're going to decrease here. So what are we decreasing? The distance jump decreases 27.6 inches for every second the sprint gets slower or slows down. That's supposed to say gets. I was going really fast yesterday. That's supposed to say gets. As the time slows down, for every second you get slower, something like that. So then if we take this idea, and if you notice that the y-intercept, this ends at 4.8. So our y-intercept is way over here at 0. So our y-intercept is way over here at 0. And this is kind of that extrapolation idea. If we go all the way to 0 and we've sprinted 0 seconds, how far are we really going to jump? I doubt we're going to jump really far, so it doesn't make sense on some of these. So really watch yourself on the y-intercept and how you interpret it. So let's move to the next piece. So what is the residual? And how do you interpret the residual? So the residual is this. It's y minus y hat. That's the residual. So it's the actual minus the predicted. And I just noticed that has one too many L's there. That's not supposed to be that way. There we go. Let's get rid of that. Whoop, 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 whoop. Let's do actual. Okay, and let's go back up to, let's just take this one right here. So I drew this on here because there's a dot underneath here. And so the residual is the actual y value for this point minus the predicted value that comes off the line. So our residuals are just the distance over or under, right? So these overestimate the value, these underestimate the value. And that's how you kind of interpret them. So it's just the distance of how far away the actual is from the predicted. And so how do we interpret these? Well, if you do the next problem here and you plug in 86,000 into the original equation on the other page, you get 11,362.52. And then that you subtract from the actual. So we get 10,998 minus 11,000. And it gives you a negative value. That negative value tells you that we over predicted because this is going to be above the actual value. So the least squared regression line over predicts the value. Okay, that's how you interpret it. All right. So how do we determine the best regression line for the set of data? The best regression line. Let's go back. First of all, you're going to use your calculator, and you need to go to page 171, and you need to practice with this data set, and you need to do the activity on there. I'm not going to walk you through it in class. I'm going to expect that you knew it because you did the work ahead of time. So on Friday, when I talk about this stuff, you're going to have to be dialed in on the calculator. So it's a regression line. So how do we determine the best regression line? This is a horrible drawing. So I'm going to take you back to, let's go back up here to the original one. And so what happens is this. You know, you guys were taught that, you know, when you're doing the line of best fit, we just kind of center the line in between these things. And in between the dots, and you like half of them are above and half of them are below. That gives you a pretty good estimate. But what the calculator does is this. It takes the residual and it draws a line, and it makes a square out of them. And it does it for every single residual that we have. So some are bigger and some are smaller. I know mine aren't very good squares, but if you guys can get the idea. So let's just call this one area 1. And let's call this one area 2. And then this would be area 3 and area 4 and area 5. So the idea behind the word least squares regression comes from the first two words. Least squares. So what really happens is this. The calculator figures out area 1 plus area 2 plus area 3. So if you really think about it, it takes the sum of all the areas and it calculates it. Well, it looks as it moves the line around, up and down, sideways, all over. It twists the line. It does all these things to it. It looks for the value that is the least amount. So it's the least sum of all the squares. That's why it's called the least squares regression line. You won't have to do that by hand, so don't worry about it, but that's how they come up with these. That's what that drawing was. I like my other drawing better. So it's just adding the areas together. It's not resistant because if I draw a line here and all of them are pretty close and that's all pretty, if I draw one way out here, this area is going to be massive. So to counteract that, I'm going to have to move the line a lot. So they're not very resistant whatsoever. So for this activity, and I'll put a picture of the solution later today. You're going to use page 171 and you're going to practice the least squares regression line. What I want you guys to make sure though is you need to go to catalog. You're going to scroll down to diagnostic on and you're going to hit enter. And that'll help you as we move along. So you're going to use your least squares regression line. You're going to use page 171. All right, let's try this one more time here. If I make it through this, we're going to be good. So a scatter plot. So let's kind of look at this here. So it's a scatter plot of the residuals. I forgot that part. Versus the explanatory variable. So the explanatory variable goes on the x-axis here. And then your residuals are plotted all over the place depending on where they are at from the distance from the x-axis. So basically what it does is assesses the fit of it. In other words, if you think about it, if I have a really good line of best fit, let's go up to here, I'm going to get some that are above it and then some that are below it. So when we look at this thing, I'm going to get some values that are negative residuals, and I'm going to get some values that are positive residuals. And it's going to look like a shotgun effect across the board. It should just be like dots everywhere. That's why I drew all those green dots. Now, so what do we look for? We look for scattering, or basically the shotgun approach. It should be all above. It should be all over the place. What we don't want is we don't want patterns. No patterns. Nothing like I did the blue here. I don't want a curve to it. I don't want them all above. I don't want them like all stuck in a corner, like anything like that. We don't want any kind of patterns. It has to be nice and solid. Shotgun approach to it. So again, you're going to construct and interpret a residual plot. The calculator does it for you. So you need to use page 178, plug in your CRV data, and see if you can come up with it. So let's talk about the standard deviation of the residuals. How do you calculate and interpret them? So first of all, the standard deviation of the residuals is based off of y hat, and this is the equation. You're never going to have to figure this out because the calculator does it for you. Again, look at page 178. It's the square root of y minus y hat squared over n minus 2, which is almost identical to our regular standard deviation, which is x minus x bar, not y hat, y bar, x minus x bar squared. Oops, and this is the sums. Sorry, that should be the sum right there, of n minus 1. So these are technically identical, except this one's basing it off of the y's. Now, how do you calculate and interpret the standard deviation of the residuals? Basically, what we're saying is if you calculate the residuals for the CRV data, use your calculator, you're going to get 972. What does that say? It says when we estimate using mileage to predict the price of the CRVs, cross off that last question there, we are off by an average of $972. That's how you interpret that. Okay, so you might be going, well, why are we calculating the y's? We're calculating the y's because if you look at what we talked about a residual, we're dealing with y values. We're dealing with all the y values. So what we want to do is we want to calculate how far the y values are away from the average y value. And that's why we get a standard deviation that way, because we're dealing with the y values. Remember, standard deviation is how far away are you from the target? Well, our target is the perfect least squares regression line. So our standard deviation falls is on how far away the actual points are from the least squares regression line. So let me go back down here. Where are we at here? Catalog, blah, 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 blah. All right. So that's how we calculate and interpret that. All right. So the last piece of the puzzle, guys, here we go. So here's the last piece of the puzzle. So we are talking about what's called R squared. And that's why I circled it here. So R squared is just the percentage. So it's just the percentage. They actually call it a fraction. R squared is just the percentage or the fraction of the variation that is accounted for by the least squares regression line. So let's talk about that. So we put these dots in a perfect linear regression. We talked about what R is. R, if they were perfect, the association or between X and Y is 1, right? So it's a perfect straight line. Well, if we square that, we get 1, which is 100%. So this perfect straight line for the LSR, or the least squared regression line, is a least square regression line is 100%. What does that tell us? That tells us that line accounts for any error at 100%. There are no errors, so it's perfect. It's 100%, right? So now what happens is nothing's ever really perfect. So you can relate R squared and R. Number one, if they give you R, you square it to get R squared. If they give you R squared, you can take the square root of it to get R out of it. So how is R squared related to S? Well, let's look at this. If all of these actual points are on my least squared regression lines, how far away are the residuals? Well, they're 0. Well, that means if they're on the line, that means their standard deviation is going to be 0. So if we have 100% accountability for the variation by the least squares regression line, then we know that the standard deviation has to be 0. So if we kind of look at that and we say, okay, well, the higher the R squared value is, the lower the standard deviation. Because what we're saying is that the lower the percentage, the lower the value of how good R is, which means that's the lower value that R squared is. So they're directly related to each other. So if this is going to be a low R, like close to 0, then our R squared is going to be super low, which then says that the least squared regression line doesn't do a very good job percentage-wise of accounting for all the errors in there. So let's talk about that real quick. This is the hardest thing. This part of the chapter is hard. You get a lot of vocabulary thrown at you. So I made this data up. You need to use page 178 to go back to the McDonald's beef catalog, which you should already have in there from the prior extent. And then you're going to make sure you use page 178 to work on the residual plots. Now, the catalog diagnostics on, make sure they're on. If they're not on, it will not give you R squared or R. You have to turn them on. Go to catalog, scroll down to diagnostics on, and then turn it on. So let's say for the McDonald's beef sandwich, we get R squared of 0.82 or 82%. So what does this mean? This means the least squared regression line accounts for 82% of the variation in the grams of fat in the McDonald's burgers. We're always stating content, and it's always the response variable. Okay? It's always the response variable. So we're really saying that even though I don't even know what the McDonald's one looks like, let's just say it looks like this. Remember, I made this one up, but you guys are going to actually do this. If I draw my least squared or my LSR right here, what I'm really saying is that once I centered this, 82% of the variation, in other words, 82% of these residuals is accounted for, or the variation in them is accounted for. And that means that this is a pretty tight line. Look at that. 0.8. 0.8 is going to, if you take the square root of that, that's going to give you an R of 0.9, which is going to be a really strong correlation. So that's going to give us a very straight line. The farther away I get from the LSR, my standard deviation gets worse. My correlation number gets worse. Therefore, this line of best fit doesn't do a good job of accounting for the variation in the line. So that's kind of the idea behind R squared. There's your video. I hope when I hit stop sharing, we have video, we have audio, and it works. Talk to you guys later.